Hi, this video is about numbers in science. So it doesn't just apply to chemistry, but to physics and any physical science that you're going to take or any science at all that you'll take. So first of all, there are two types of numbers that we need to think about. One are exact numbers. Exact numbers, you know their value exactly. They're usually definitions, something like there are 60 seconds in a minute or 1,000 grams is in a kilogram. Now, if you're counting objects, that's also an exact number. So we have exactly 24 students in the class. That 24 would be an exact number. Now, inexact numbers comes from measurements, and they have some uncertainty. So why measured values have uncertainty comes from human error. The equipment could not be calibrated properly. If you want to try to minimize the equipment error, always use the same piece of equipment throughout an experiment. So if you get an initial mass using a balance, make sure you use that same balance throughout that experiment. But inexact numbers are measurements because they have some uncertainty. Now, again, this is just some vocabulary. Precision and accuracy are ways to describe the measurement, and precision is how closely the individual measurements agree with one another. So here's this dartboard analogy, and you see the three darts are landing at approximately the same place. So that would be precision. Now, it's not in the bullseye where supposedly that's where you want your darts to be. However, they are very close to one another, so this would be precision. Where accuracy is how close the measurements agree with what they call the true value. And if we continue our bow and arrow analogy and dart analogy, the bullseye would be our true value. And so these four arrows are close to the bullseye, and so we would say that this is an accurate display, and it's also precise because they're close to one another. All right, now let's look at some data. So they're supposed to determine the density of mercury, which is 13.6 grams per milliliter. That's the true value. That's what's reported in the literature. All right, now we're not going to ever do this experiment because we're not going to use mercury in high school. However, let's just pretend that we did. And Michael came along and he had 3 trials, and he had 14.7 grams per milliliter, 14.9, and 14.8. Now, those values are very close to one another. So Michael was very precise in his measurements, but he wasn't very accurate because 14.7, that's a whole unit off from the accepted value of 13.6 grams per milliliter. Look at Brittany's data in her 3 trials, 13.6, 13.7, and 13.5. Her data is very accurate, and it's also very precise. And finally, Priya, 14.7, that's not very accurate. 13.6, well, that is accurate. And then 12.7, not very accurate. And if you look at her 3 trials, they're not very precise. All right, so let's talk about uncertainty in measurement. Now, let's pretend we have a balance that measures to the nearest 0.0001 gram. We have one balance like this in the lab, but most of our balances report to the hundredths place. So this would be a very expensive balance. And you put something on the balance pan and it reads 6.7842 grams. Now you could report it as 6.7842 plus or minus 0.0001 grams. But we don't even have to say that plus or minus notation because in science, the last digit that is reported is uncertain. So important. This is very, very, very important. In a measured quantity, you will report all the digits of which you are certain, and you will add one additional digit that you have estimated. And so if you're getting a volume in a graduated cylinder, let's say the graduated cylinder goes to the nearest tenth of a milliliter, you will estimate the hundredths place, and you would report that uncertain, that estimated final digit. We're going to practice this in the lab. Now let's talk about significant figures. Some people abbreviate this and say sig figs or significant digits. Now the definition of a significant digit or a significant figure is all the digits of a measured quantity including that uncertain one. So the uncertain digit is a significant digit. Now, let's just pretend that you're looking at a measurement right now, and they're going to ask you, well, how many significant figures are in this measurement? Well, if it's not a 0, if it's, 1 through 9, that number is significant. But zeros, there are some special cases. There are 3 types of zeros. The first type of 0 is what we call a leading 0. So let me see. Okay, here we go. Sorry about that. A leading 0. A leading 0 is never, ever significant. And a leading 0 is just like the name implies. It's at the front of the number. It leads any other number. So if we had this 0.00202, these zeros are leading, and they are not significant. So we would say that this number has 1, 2, 3 significant digits. I like to think of leading zeros just as a placeholder for the decimal point. What would even be better for this is to write it in scientific notation, 2.02 times 10 to the negative third. All right, so 3 significant digits in that number, in that value. Now, this has something in it which we call a sandwich 0, which means that it's between 2 non-zero digits, and you do count sandwich zeros all the time. So this value has 3 significant digits. Now, trailing zeros are zeros at the end of a number, and sometimes they're significant and sometimes they're not. They are significant when there's a decimal point in the number. So, for instance, let's look at this number, 20. Is there a decimal point in that number? There is not. And so we would say that that has 1 significant digit. If we said 20 and had a decimal point at the end, now that looks weird, but what that decimal at the end is telling us is that that 0 is significant. So that would be 2 significant digits. A better way to have done this would have been to say 2.0 times 10 to the 1. And here, we've got a trailing 0 and there's a decimal present. So yes, indeed, it is significant. So there would be 2 significant digits in that value. Let's look at something else. Let's do 0.002020. Got every kind of 0 here. Leading zeros, not significant, not significant, not significant. That's a value. 2 at that digit is significant. A sandwich, significant. Digit that's not a 0, significant. Trailing 0. Ask the question, is there a decimal point present in the number? Oh, there is. So we're going to count that. So this value would have 4 significant digits. We could have made it even a little bit easier had we written it with scientific notation, which would be 2.020 times 10 to the negative third. Okay, we're going to practice with significant figures as well. All right, now, how do we use these significant figures in calculations? All right, well, keep in mind, the least certain measurement, the one that you have the least number of significant digits, is going to limit your answer in the significant digits. So there are 2 different rules for sig figs. So here we go. The multiplication and division rule. Let's look at this first. All right. Your result is going to contain the same number of significant figures as the measurement with the fewest significant figures. So let's just go ahead and say that you're getting the volume of something. And the length you measure, somebody reports as 2.1 centimeters. And then somebody comes along and says, well, that's the length. And somebody has a different ruler and says, well, the height is 2.20 centimeters, and then someone says, well, the width, and they have a completely different ruler, which is, and they say that it's 3.21 centimeters. If you want to get the volume of this, we're going to multiply these 3 numbers together. And we have centimeters all around here. And what you have to do is you have to say, how many sig figs in this number? 2. How many here? Trailing 0. Is there a decimal present? Yes, there is. Oh, 3 sig figs. And how many here? 3 sig figs. All right. So our answer, the unit, is going to be cubic centimeters. And our answer will have the least number of sig figs that we had in our measurements. Our answer will only have 2 significant digits. And I didn't multiply this out. So let me see what I get here. I get 2.1 times 2.2 times 3.21. My answer, my calculator gives me this crazy answer. So my calculator says 14.8302. All right. But we want to report our answer to the correct number of significant figures. We can only report to 2 because this value here only had 2. This measurement only had 2. And so let's go ahead and we can round that 14 to 15. And that is how we should report that answer. All right, again, we're going to practice with this. The same thing happens in division. All right, now addition and subtraction is a little different. We look at decimal places, and so the result has the same number of decimal places as the measurement with the fewest decimal places. So if we do this, let's go ahead and say that we used one balance and we had 3.21 grams. And then we use the same balance, so we're using good lab practice, and it's 10.72 grams. And then our third object we report as 0.1 grams. Now we want to add all this together. Okay, so here we go. We get 14.03 grams, but how should we report it? We can only report it to the tenths place because this hundredths place here is empty. So we have no idea what that number should be there. You can't just assume it's a 0. We don't know what it is. So we cannot report this place. And so it would be 14.0 grams, or our answer would have 3 sig figs. So notice the difference in rules between addition and subtraction and multiplication and division. And again, we're going to practice this in class. Okay, now exact numbers. So we started this video with exact numbers. They will never limit your number of significant figures. So if we're doing a problem and we're doing a conversion and we use that there are 1,000 milliliters in a liter, that 1,000 is not 1 sig fig or not 4 sig figs, it's infinite because it's an exact number. If you've counted something like there are 10 pencils on the floor, that 10 is an infinite number of significant figures, and it will not limit the number of sig figs in your calculation. All right, so we're going to practice all of this in class. So we'll see you then. And one last thing, if you notice, I waited until my final answer to round to the correct number of sig figs. All right, well, tomorrow we're going to learn about dimensional analysis.